Hi everybody, this is Mr. Short. Just as a reminder, in the previous lesson we learned about valence electrons. We related valence electrons, electrons in the outermost energy level, to an element's main group number. The main group numbers are 1, 2, skip a few, 3, 4, 5, 6, 7, 8. We also learned that the horizontal period number, 1 all the way down to 7, the horizontal period number tells us the number of energy levels in a Bohr atomic model. Today what we're going to learn about is called abbreviated noble gas electron configurations. Alright, we're going to start by learning about what are called the S and the P blocks on the periodic table. And remember, there are S and P sublevels that we've talked about with electron configurations. The S block includes the two main groups that are farthest to the left. It's going to be these two over here. And recall that S sublevels can hold 2 electrons. Okay, so this right here would be the S sublevel. Also remember that when we write an electron configuration, it might sound kind of like this: 1s2, 2s2, 2p6. Okay, p6. P block includes those 6 main groups that are farthest to the right, these over here. And again, recall that P sublevel can hold up to 6 electrons. And again, this right here would be the P block. Now if you're interested, there is a D block and an F block. The D block is right here, and the F block is down here. You can label those on your sheet also if you'd like. But I think in this class the most important are knowing a little bit about the S and the P block. Okay. Next thing that we're going to do is going to be to address this guiding question right here, and it's going to take a lot of thought on our part. So I'm going to kind of move around between some different things that we've learned about, go back to the previous set of notes, and we'll get an answer to this question, which is about prediction. So the guiding question says, how are ending electron configurations predicted for elements in the S and the P blocks? Here's what we're going to do. We'll write down the element's horizontal period number. We'll write down the block that the element is in, either the S or the P block, and then we'll write down the column within that block. Okay, so the numbers could be 1 or 2 if it's in the S block, or it could be 1, 2, 3, 4, 5, 6 if it's in the P block. Okay, for example, sodium is right here. So you should ask yourself, what horizontal period is it in, what block is it in, and what column inside the block is it in. Give that a try, hit pause and write it down. Okay, you should notice that the horizontal period is 3. 1, 2, 3. So it's in the third period, it's in the S block, and it's also in the first column of the S block. Sorry about that. I had to hit pause because there was an announcement over the loudspeaker. So we're talking about sodium. Sodium we would predict would end in 3, third period, S block, and 1 because it's in the first column of the S block. So let's go back and take a look at this. So our prediction is that it's going to end in 3s1. Now here's the complete electron configuration for sodium. And you can see in fact that it does end in 3s1. Let's practice and review electron configurations a little bit real quick. Remember, you have to follow the order of electron configuration. And that order always goes 1s, 2s, 2p, 3s. So we've followed that order. Also, any S sublevel has to be completely filled up with 2 electrons before remaining electrons spill over to the next sublevel. So if we're going to spill electrons over to the next, this has to be completely filled up. If we're going to spill electrons over the next, this has to be completely filled up with 6 electrons. And remember, the sum of the exponents has to add up to the total number of electrons in the atom. Sodium is element 11. 2 plus 2 plus 6 plus 1 adds up to 11. Let's try the same thing with sulfur. So I want you to predict the ending electron configuration for sulfur right here. Here's sulfur. So I want you to hit pause and predict its ending electron configuration. Okay, we would predict that sulfur would end in 3, because it's in the third horizontal period, 3p because it's in the p block, and it's in the 1, 2, 3, fourth column within the p block. So we would predict it ends in 3p4. Now keep in mind, it's got 16 total electrons. Okay. Here is the complete electron configuration for sulfur. And in fact, you can see it does end in 3p4. Okay. Again, a double check. We want to make sure that the sum of the exponents adds up to 16. So 2 plus 2 plus 6 is 10, plus 2 is 12, plus another 4 is 16. Let's do the same thing with rubidium. Rubidium is here. So predict its ending electron configuration. Push pause and make that prediction. Okay, we would predict that rubidium would end in 1, 2, 3, 4, 5, S, 1, because it's in the fifth period, the S block, and the first column in the S block. 5S1, and we need the sum of the exponents to add up to 37. And in fact, you can see it ends in 5S1. And when we take a minute and add up these exponents, 2, 2, and 6 is 10. Another 2, 6, and 2 is another 10. So right there we've got 20, 30, 36, 37. All right, same thing with silicon, Si. Hit pause and make a prediction about its ending electron configuration. Okay, we would predict that it would end in 3 because it's in the third period, P because it's in the P block, and 2 because it's in the second vertical column within the P block. So 3p2, and we want the total exponents to add up to 14. Okay, so again, the purpose of this is predicting ending electron configurations. We accurately predicted that it ends in 3p2, and the sum of the exponents do add up to 10. 2, 2, and 6 is 10, 12, 14. So we've done that right. Okay, now what we're going to do is we're going to move on to the heart of this lesson, which is about noble gases. So noble gases are the elements that are located in main group 8. And we already talked about the fact that they're located in main group 8 on the previous page. Remember, since they're in main group 8, they're all going to have 8 valence electrons, so they've got a stable octet of 8 valence electrons, and that's going to be important to us in just a minute. Okay, I want you to hit pause in just a second, and I want you to predict the ending electron configuration for both neon and argon, which are both group 8 noble gases. Okay, take a minute and predict the ending electron configuration for neon and argon. Okay, for neon, we would predict it ends in 2p6, and for argon, we would predict it ends in 3p6. I'm going to take a second and I'm going to write those down. So this is 2p6, and then likewise, argon is going to be 3p6. Let me get those red so that we can see those a little bit better. Okay. We want to check that and confirm that that is the ending electron configuration. We can go ahead and write out the complete electron configuration. There it is, 1s2, 2s2, 2p6. So our prediction was correct, and the sum of the exponents does in fact add up to 10 electrons. All right, our prediction is argon ends in 3p6. We can confirm that by writing out a complete electron configuration. It does in fact end in 3p6. And the sum of the exponents, 2, 2, and 6 is 10, 12, 18, does in fact add up to 18. Now, this is fairly time consuming to write out a complete electron configuration, but if we're good at making these predictions, and if we know a little bit about noble gases, we can write a simple abbreviation. Here's how we can abbreviate 1s2, 2s2, 2p6. We say bracket neon. bracket neon means 1s2, 2s2, 2p6. So if bracket neon means 1s2, 2s2, 2p6, then you might predict that bracket krypton means 1s2, 2s2, 2p6, 3s2, 3p6. So instead of writing out this complete electron configuration, we can do a little bit of substitution, and we can now substitute bracket neon to mean the first 10 electrons ending in 2p6, and bracket krypton to mean the first 18 electrons ending in 3p6. Okay, now what we're going to do is a little bit of abbreviation as a time saver. Now down here below you can see for sodium, sodium ion, chlorine, and chloride ion, I've already got the complete configurations written out. But what we're going to do is a little bit of substitution, and I'm going to ask you frequently to pause it, make a prediction, and then check your answer. So right here, for example, you can see that the complete abbreviated configuration, the complete electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. I want you to hit pause and think about how we can abbreviate that using neon as a substitution. Okay, what we're going to do is we're going to hit bracket neon to mean the first 10 electrons ending in 2p6, and then we just have to add in 3s1. So remember, bracket neon means the first 10 electrons ending with 2p6, so we just continue it on with 3s1. And that's a nice time saver. Now, take another minute. See if you can do some substitution to figure out the abbreviated noble gas electron configuration for sodium ion. So the abbreviated configuration for sodium ion would be just bracket neon. Because bracket neon means the first 10 electrons ending in 2p6, do you see how sodium ion has an identical complete electron configuration to that of neon? So we can just abbreviate it as bracket neon. Okay. Try some substitution for chlorine. Now chlorine has 17 electrons. You can see it ends in 3p5, and the sum of the exponents adds up to 17. Well, bracket argon would mean the first 18 electrons, so we can't use argon yet. We've got to use bracket neon, and then we've got to continue on from there. Bracket neon ends at 2p6, so we need to add in 3s2, 3p5. So 3s2, 3p5. Okay, and again, this means 10, there's 12, plus another 5 is 17, adds up to 17 right over here. And that's how we abbreviate it using abbreviated noble gas electron configuration. All right, see if you can do some substitution for chloride ion, which ends in 3p6. Okay, chloride ion should be really easy because look, it ends in 3p6. It's got 18 electrons. Argon also has 18 electrons, and it also ends in 3p6. So the abbreviated noble gas electron configuration for this is just bracket krypton. And that's how simple it is. So what I want you to understand is that when atoms turn into ions, if those atoms are in main group 8, they will look like a close noble gas because the close noble gas has 8 valence electrons. Look at this one right here has 8 valence electrons. It's these 2 plus these 6. This one has 8 valence electrons. It's these 2 plus these 6. So again, when a neutral atom turns into a charged ion, if that neutral atom is in one of the 8 main groups, it will always look like a close noble gas, so it will have an abbreviated noble gas electron configuration as one of the noble gases. All right, thanks a lot. See you guys soon.